Questions? Nothing? You guys can do all of 1, 2 with no problem. If I had a pop quiz on it. Truth tables are okay? All right. You guys are all good with that. So what we had stopped on propositions is propositional logic. We had the mathematical object was declarative statements, propositions. And we had all the rules that went along with this, which is the whole and, or, not, implies, if and only if, along with parentheses and orders of operations and everything else. What we hadn't done at this particular point was the idea of what does it mean to be the same. And really, when we're talking about the same, we're needing some way to compare. And if I was going to look at compound propositions and I ask, okay, how do I compare two compound propositions? And so if I would have compound proposition, say, version 1, if I want to say, let's say I wanted to compare, let's make something that doesn't necessarily always look clean. Say the entire compound proposition of P implies R or Q implies R. And I would like to compare this to, say, P and Q implies R. You'd want to do a comparison of some sort where we're just looking at compound propositions. And one of the things that we would obviously say that if I am going to compare things where I'm using propositional variables, where the variable can represent any possible proposition, we ought to use the same variables, which is really saying that you're using the same proposition in comparison. So if one side's talking about the bears, the other side better be talking about bears. So if we're going to do this, there's certain things that need to come along with the problem. One, if I am going to, if you do compare, the first thing is we need to have same propositions. In other words, you better denote them the same. And this would be the same as like when you guys did your homework and I said it'd be smarter to use, instead of P, we'd actually use the word bear, etc., and the word safe. But on the other hand, if you would like to compare your work to somebody else's work, you would say, well, we actually do have the same proposition, right, as we're going through it. So you may better make sure that you're using, whether your labels are, that the propositions are the same. The second thing that I'd like to have is that we're going to compare same conditions. If you're going to have same propositions, we'd like to have same conditions. When is this compound proposition true under what conditions? When is this one true under what conditions? In other words, this would tell you that if I made a truth table, the rows better match up. That as you look at it, they don't have to necessarily look the same, but when I'm considering, say, P, Q, and R, true, 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 I want to consider true, true, true. So I'm going to compare my 3 true row versus your 3 true row. If I have true, true, false, then I want to compare true, true, false. And so the 2 true and the 1 false rows, no matter which order they're in, you say, okay, of these 8 possible rows, I'm going to make sure I'm going to look at the right ones at the right times. And now if both of those are met, you know, it would make sense to say that same would mean same conditions give same results. Same input causes the same truth. Same input causes the same false. And really gets down to, if we're going to do this, do we have anything in place to say that, okay, if I'm going to say the left is the same as the right, that means that the exact same truth values of the left, which we would have P, Q, and R, right? You would say when P is when P is true, Q is true, and R is true, that whatever the left-hand side is, that when P is true, Q is true, and R is true, it would be the same thing. So if the left was true, the right would be true. Now, if we would pick true, and R is false, then true, and R is false. Whatever happens on the left is what should happen on the left. And I need to do that for every condition as we go through it. Well, one way to do that would be to simply make a truth table, right, for both of them, and make sure that the rows align, and then say, are the truth values the same, but do we have an operator that tests for when you have a true, do you have a true, and when you have a false, you have a false, but if they don't match, it returns false. What operator does that? The biconditional. The biconditional is true only when you have true in the same place, false in the same place. If they are not, the biconditional returns a false. So we could use the biconditional to operate on that. Some little bit of background in terms of words. If something is always true, this denotes what we call a tautology. 2. If something is always false, we denote this as a contradiction. Sometimes I wonder, the English word contradiction has a couple of applications of it. For the English word contradiction, when we're dealing with something of that nature, a lot of times you say, well, that's impossible. That's not what we're talking about. Right? What we're talking about that is if you would take all possible conditions and it always ends up being false, that particular compound proposition is called a contradiction. One of those things that you say is impossible just simply says all possible inputs returns false, like it's always a lie. So like you would say things like can't happen. But one of the issues with contradictions and features of it under logic, it just simply says that all inputs return a false. But if you would get into, the idea of a lot of people try to think in terms of like physics or other aspects. That's not what we're talking about. It's just a truth table. When I look at it, it's false all the way across. Tautology, true all the way down, right? On the other hand, the third possibility is sometimes true, sometimes false, and this is a contingency. The idea behind contingencies is, okay, you would look at it and say, under certain contingencies, it's true, and under some certain contingencies, it's false. Examples of things like this is if I would consider what is P or not P. If I make the truth table, I only see one variable, so I'm only going to have 2 rows. It's either true or false. What would not P be then? False, true. And then what would be P or not P? What's true or false? True. What's false or true? True. So this is called a tautology, which would make sense. I'm standing or I'm not standing. That's always true, right? On the other hand, if we would go, what is P and not P? Well, again, P is true, false. Not P is false, true. P and not P. What is true and false? False. What's false and true? False. And so that would be a contradiction. So that is a contradiction. And this one here is a tautology, which would make sense as well. I am standing and I am not standing. That's always false. And a contingency is like, well, pretty much all the normal truth tables you do. Sometimes it's true, sometimes it's false. All right, now that we know we have that, we can actually get to a definition. of this idea of sameness, and so the idea of sameness, it's kind of looser than equality, so we're going to use the word equivalence, and so that'll be our definition. We have compound propositions. Now, compound propositions are usually long and messy, like I kind of wrote here at the beginning, right? Like that P implies Q or Q implies R. If I would say P and Q implies R, we would look at those particular things. But I don't know what compound proposition is. I don't know if I have 1,000 of these variables, 1 of these variables, 10 of these variables. And so normally we would just take any compound proposition and say PQ. What does P represent? A compound proposition. You could imagine that there's a lot of stuff that is being stored within this P. I don't care what it is, right? So compound propositions PQ are called logically equivalent. Okay. Logically equivalent if the exact same initial conditions cause the exact same truth values. But we have a test for that. What we're going to do is say these are going to be logically equivalent if you would go ahead and compare their biconditional. Create a larger compound proposition, right? Take whatever you have for P, take whatever you have for Q, put an if and only if between them, and make a truth table. And if I see this truth table is a tautology, again, what does the biconditional check? The left is true when the right is true. The left is false when the right is false. That's exactly what I wanted. If they're true in the same places, false in the same places, the biconditional checks that. It ends up saying, yes, it's absolutely true. Then we're done. They're logically equivalent, and we use the following notation. P is logically equivalent to Q. We use something that kind of looks like an equal sign. We just use 3 lines. So whenever you see a triple line, what that really means is that I put a biconditional in its place, made a very large compound proposition, checked out its truth table, and it ended up being a tautology. And that's kind of important. A lot of times, you get to a problem and say, let's do a classic example. How about, might as well just do one of the De Morgans. Say P and Q versus not P or not Q. If I want to check these two, this is the way that we check it. All right, I'm going to check not P and Q biconditional with not P or not Q. So I make this larger compound proposition based upon my 2 compound propositions. And so we only have P and Q, so PQ. So we have true. We've got true, true, false, false, true, false, true, false. Obviously, I'm negating both P and Q, so we got our not P. And actually, I can just simply do that in our head. We've got not P or not Q. Let's just do that at once. What is not P or not Q? What's false or false? For true, that'd be not P, not Q, right? So false or false? False. False. False or true? True. True or false? True or true? So it's false, true, true, true. This is another reason why I said you have to have that truth table down, because we're just going to march right in it. And if you can't get, even to the point where I've had people like You're still trying to get down the logical operators by the first exam. It's too late. Right? Like I said, the day after I presented this, you should have gone home and had these down solid. There shouldn't be pausing on these. You should, all right, I know what these mean. All right, eventually we're going to compare this. What is P and Q? True and true is? True and false? False and true? False and false? So that would be just simply true, false, false, false. I'll eventually do a not P and Q, which is just negate that. We get our false, true, true, true. And now a lot of students will simply, no, I'm going to make you go one more step. A lot of people sit there and say, oh, look, same. Therefore, I'm done. Okay. I know some people say, why do you want to go to the one next step? It's because pointing your finger and saying same, it doesn't show logical equivalency. What shows logical equivalency? The biconditional is a tautology. So you just go to that one extra step and show that the whole not P and Q logically, biconditional with the not P or not Q. And then you would just say, okay, false if and only if false is true, true if and only if true is true, true, true. That's a tautology. All right, so you're given a tautology. That tells us that, oh, I can go ahead and say that not P and Q is logically the same as not P or not Q. And we can sit there and say it doesn't matter what P and Q are. It's not true that my name is Mark and it is a cloudy day. That's the exact same thing as saying that I'm not Mark or it's not cloudy. Those mean the exact same thing under logic. All right, what's the purpose of all these things? Why? Why are we interested in of which we're going to get a bunch of these here in a bit. Why are we interested in them? Well, we've done a lot of equivalencies before, like in college algebra, right? One of the things in college algebra, we say, here's a algebraic expression, and we replace it with a equivalent algebraic expression. You would say, well, these are the same under the exact same conditions. And so one of the ideas of using these things is really down to a question of simplification. Or manipulation of expressions. I give you a compound expression, say it somehow differently, but have it mean the same thing. So symbolically, we would simply say that, okay, I don't want to write it like the left. I'll rather write it like the right. Or I don't, again, these go both ways. I don't like the left, so I'm going to write it like, sorry, I don't like the right, I'm going to write it like the left. One way of looking at this is this is a form of distribution. The negation goes through. It distributes. But what do you notice about the distribution of negation? What does it do to conjunction? Flips it. It makes it into disjunction. And if we did De Morgan's, it would make a disjunction into conjunction. And so De Morgan's laws, and we'll get into those, are actually a form of distribution. And we're actually going to have 5, 6, 7, 8 distribution laws. 2 of them are going to be called De Morgan's. 2 of them are going to be called distribution. The other 4 don't have a name, even though they are distribution. And some of them behave in kind of some really weird ways. In college algebra, how many distributions did you memorize? 1. Right? But again, these are just symbol manipulations according to laws. And so when we have in 1.3, The logical equivalencies that are considered useful or usually get their title law. Useful really means used a lot. Logical equivalency. We will call this a law. All right, what are some laws that we have from 1.3? We have the laws based upon the and, the or, and the not based laws. I think this is the first table in the textbook. And what you'll notice is they only use, and none of these laws that they have are the exclusive or. Exclusive or is rare enough or used only in special cases that it doesn't get called useful enough to get a name. Even though there'll be lots of logical equivalencies for the exclusive or. And you might actually have to make some of them when you need it. But on the other hand, we don't write them down on a table because they don't consider, oh, you don't run into this all the time. It's a special case. Worry about it then. We don't have to memorize it. Yep.
Should it be considered a law, an exclusive or, in those in the notation of ors and nots? Because I mean, it's just like a definition, like we've rewritten.
Well, when we do things like laws, like what we just did, right? P and Q is logically the same thing as not P or not Q. We also can show that not P or Q is logically the same as not P and not Q. And you can show both of these by tables. We'll also be able to show things like P exclusive or Q is logically the same thing as not P if and only if Q, right? And we'll be able to show that. That gets no name, right? It's things that you can show with the truth table, but the word law really just comes into play that we do it enough, let's just go ahead and give it a name. It's like an honoring system.
The reason why I was saying it might not be considered a law because aren't you like defining a new symbol with your old symbols in here?
No.
Because aren't your like base symbols?
Nope.
Or
No. For all this is arbitrary. I mean, we get to pick names just because we do it a lot. I mean, we don't even have to use. Eventually, when we get to Boolean, like I said, none of these only one symbol is necessary. We only need one real operator to do everything. But we use more. Why? The more complicated your operators, the easier it is to write your symbols. The simpler your symbols, the more complicated your propositions. It's like really, really hard to say if you use only one thing. It's like designing circuits with only the NAND gate. Can you do that? You can do everything you could ever possibly do with a NAND gate or a NOR gate. Why would you want an AND and a NOT and maybe a conditional gate? Because it's easier to do. It's a more complicated computational system, but on the other hand, boy, it's writing it or designing it is trivial the more complicated the tool you have. It's like kind of the idea of spending some effort up front. I mean, you could, any know the difference between CISC and RISC in terms of CPU structures? Should your CPU do everything, like have a sign function built into the processor? Or should the only thing the processor do is a bitwise shift and a bit add? Make it a super, super simple processor and then do everything before it hits the processor? Or should you say, I make a super complicated processor and I just throw stuff at it and it's able to do it? It's reduced instruction set versus the more complicated instruction sets. Well, it's half a dozen of one or six of the other. It's how we work it out. So the hard part is kind of there's a lot of tradition that goes into things. For all of these, like the one I'm just about to erase, it really gets down to if it shows up a lot, maybe give it a name. If it doesn't, you can always show it and know it, right? But logical equivalencies for each of these just says that the biconditional, same conditions cause same values, and if it shows up enough, like this one, this is De Morgan's law. So we have De Morgan's laws, we have the identity laws, that P and true is still P. We have that P or false is still P. That's identity. The identity is very useful. It's the do nothing. A lot of times when we talk about simplification of propositions, of compound propositions, the do-nothings are very important. Like when you solve things in college algebra, it's all about inverses and identities, over and over and over again. Well, we need to know what the identities are. Not all operators have an identity. Both the conjunction and disjunction have an identity. Not only that, P or true is simply true, but P and false is false. That did the opposite. If I and a true, nothing happens. If I or a false, nothing happens. But if I or a true, it's just true. I've completely lost the proposition. If I and a false, it's false. I've completely lost the proposition. So instead of a do-nothing, it's a domination. And that's why they're called domination laws. We also have the P or P, just say P, P and P, just say P. That's idempotent. All right, what are the idempotent laws? It's the say it once. My name is Mark and my name is Mark. Please say it once. My name is Mark or my name is Mark. Just say it once. That's what the idempotent law is. So we have domination, we have identity, we have idempotence, we have De Morgan's. Again, De Morgan's is a form of distribution. So I kind of had it a little bit early here. Normally you introduce the distributions all together. We also have the idea of, we've already done this. It's not true that my name is Mark is the same thing as saying my name is Mark. It's a double negation. This is what we used to handle the liars. Make a liar lie about his lie and he would get the original values back. That is double negation. Other logical equivalencies, commutative. P and Q is the same thing as Q and P. P or Q is the same thing as Q or P. The and the or and the exclusive or are commutative. Is implication commutative? No. If you'd make as truth tables, you could see one is, if we'd set it up the way I normally do, true, false, true, true. The other one would be true, true, false, true. Right? Those aren't the exact same in the same conditions. And so that's true of, if we think of other operators, are all operators commutative? For example, under normal arithmetic, is addition commutative? 1 plus 2, 2 plus 1? 2 times 3, 3 times 2? How about division? No. How about subtraction? Not all operators are commutative, just some of them are. We have to know which ones are and when do they actually apply. We also have associative laws. We could have that P and Q and R is the same thing as P and Q and R, but on the other hand, P or Q or R is logically the same thing as P or Q or R. If I mix operators, there is no association. Right? As long as everybody is and this actually allows that when you have association and commutativity within a single operator, normally what you do is you could say just drop the parentheses because order doesn't matter. You can rearrange it however you want. The big deal about these are you have to do 2 at a time. Right? You can't do all 3 at once. Q without a parenthesis, P and Q and R really doesn't make sense because you're asking, well, who goes first? But what happens is because it's associative and commutative, it doesn't matter. So group however you want, and you'll get the same answer because of that whole, I can flip it and rearrange it under association, and there wouldn't be any problem. And that's why if these 2 things happen, you can drop parentheses. So associative, commutative. Let's go ahead and do the other distributive. What if I would have a mix of op? What if I would say P and Q or R, or a P or Q and R? What's nice about this, and also bad at the same time, is we think about the idea of multiplication, like 3 times x plus y. That's 3x plus xy, right? Distribution is everybody on the outside distributes to everybody on the inside of the parenthesis. this is also true, and the op goes with it. And so if I would distribute, this becomes P and Q, or P and R. And if I distribute, this would be P or Q and P or R. So it fully distributes through, except we have two distributions because we have two ops of same level. Whereas when we had normal college algebra, you only had times and plus, right? Because minus is really a plus if we define it as negative numbers, if we allow negative numbers. And division is really multiplication if you allow reciprocals. So as long as we have the reals, we only have times and plus. And so, but here we have a lot more ops and two at the same level, so we have to worry about it. This is a very good example of, obviously, if you didn't have parentheses, what in the world are you talking about? Do you mean, and this is also cited as well. Is and commutative? Yes, so this could actually be Q or R and then and P. So I could have left-hand distribution and right-hand distribution, but because of commutativity of conjunction, they'll end up being the same thing. And then really what this would be Q and P, R and P, but it's the same as P and Q and R and P as well. So it really doesn't matter because of the commutativity feature. So we can put this on the left, we can put this on the right. The question is if you mix ops, distribution happens. Now, normally we kind of think of logically equivalent means both sides are the same. In college algebra, if we would have things like this, say 3 times x plus y is equal to 3x plus 3y, right? Sometimes we go this way, and we use the word distribution. Sometimes we go this way, and we use the word what? Factor. But what is factoring? It's distribution, right? You're using the distributive law. We just don't say it. We say we have a special case of if it's going from a product into the product gets distributed through, we use the word distribute. If we try to go the other direction, but that's still the distributive law. If I try to use the distributive law kind of in the backwards way, not backwards, but from the right to the left, we'll give it its own special name, factoring. Same thing happens. Sometimes you're interested in left to right. Sometimes you're interested in right to left. But you have to understand that both are logically equivalent. And it gets at why would you do one or the other? I don't know. Pick one. Sometimes you're wanting to, especially since this is human language. If you think of that first one, we would say things like bear, safe, and ripe berries, right? Either you saw a bear or make a long pause. Long pauses designate there's a parenthesis somehow. Either you saw a bear or it was safe to hike and you saw ripe berries. On the other hand, you could rather say you saw a bear or it was safe to hike and you saw a bear or you saw ripe berries. Those are logically the same sentence. Why would you pick one or the other? Well, which one sounds better? That's really what it gets down to. Which one sounds good? But again, we still have picking one or the other. If you have one, you form the other, you might call it distribution. If you do one and the other, you might call it factoring. All right. So we've got distribution. We've done De Morgan's. How about, well, the one I did at the very beginning. That whole, what is P and not Q, not P? That's logically what? My name is Mark and it's not the case my name's Mark.
Contradiction.
Contradiction. That's always false, right? On the other hand, if I have P or not P, that's always true. And these are just simply called the negation laws. And then the last one I'd like to do is one of those ones that you kind of look at it a little bit and you have to think. You have P or you have P and you have Q. You have P and you have P or you have Q. All right, let's think about that for a second. Or you have P or you have P and Q. So you have an apple or you have an apple and an orange. What do you definitely know? You have an apple. That's logically the same as just simply saying you have an apple. What if I said you have an apple and you have an apple or an orange? Who cares about the orangeness? You said you had an apple and you have an apple or an orange. Well, I have an apple, so I definitely still what? Have an apple. This is called absorption. What happened to the Q? It got absorbed. It's kind of interesting. It's one of the few ones where when we look at it, you have this compound proposition, and one of them just simply gets absorbed by the other, even though they're not talking about the same thing. One's talking about apples, one's talking about oranges, but in this condition, the orange is meaningless. All right, so that's the ands and the ors and the not ones. The other two are the ideas of what about implication. Let's go ahead and add the imply and the biconditional. What do those laws look like? There's several in the textbook. I'll box out some ones that are really important. The first one is that P implies Q is logically the same as not P or Q. We've also seen this before in the textbook as Q or not P, except they use the word unless. That was that unless version of implication. So they actually had it, and they said, well, you know, it's like, what does the word unless mean? All right, it's actually this guy. It's one of those ones where we look at it and say, does this really make sense? That if my name is Mark, then I'm teaching the class. It's this exact same thing as I'm not Mark or I'm teaching this class. Again, how would you show this? You could show this with what? A truth table, right? Just show it with the truth table. And these are logically the same. These are ones. The right-hand side is what I normally term as the disjunctive version of implication. Like write and implies as a disjunction. This is how you do it. So do we actually, now comes that question, do we really need implies? Every implies is actually a what? A disjunction. So you could always write it as an or, but on the other hand, implication gets used a lot, so we just go ahead and use it as its own operator, even though it actually is an or. It's not the first or the second. All right, a second one that's rather important is P implies Q is logically the same as not Q implies not P. If I gave you P implies Q, what would we call the not Q implies not P thing? It is the contrapositive of the original implication. This tells us that implications and their contrapositive are identical, logically. Another one is actually a combination of two. And this is, I'll go ahead and use this as a rule. What is not P implies Q? Well, first off, this would be logically, if I would use older ones, right? Use older logical equivalencies. What is P implies Q? From number one, what is P implies Q? Not P or Q. So this is actually not P or Q, right? I just replace something with its logical equivalencies. What would De Morgan's law allow me to do? Take that not and distribute it, right? So that would be not P. What would happen to my or? And not Q. De Morgan's is a form of distribution. It's just that the and the or flip over. But what's not P? P by the double negation law. And you could write down every law that you used. Right? You could say, oh, I use this. Oh, I use this. And so in the end, this is simply what? P and not Q. It's kind of important. This is also another big one. To negate an implication is to say that you have the first and not the second. Other words for an implication, the left-hand side is sufficient, the right-hand side is necessary. The left-hand side also is sometimes called the hypothesis. The right-hand side is called the conclusion. So a not implication is to say that you have the hypothesis and you do not have the conclusion, are logically the same thing. What's nice about this is implication is always a little bit awkward. Conjunction is nice. Because who's a dominator of conjunction?
False.
False. So if there's ever a false, this entire thing is false. In false, things that are always false are just as useful as things that are always true. Because you just flip it, and it's true. So this is one of those things where, oh, what if I look for a thing that's always a contradiction, always false? If it ever shows up, the entire thing is false. Distribution laws. There's 4 of these. What if I would have P implies Q and R? What if I had P implies Q or R? These are nice in that it does really what we would expect. This is P implies Q and P implies R. This is P implies Q or P implies R. It does exactly what you would expect, right? The implication just goes right through, and stays and or stays or. On the other hand, if we have flip order and implication is non-commutative, so it actually has to have its own rules. What if I have P and Q implies R? What if implication, right, occurs second? And what if I have P or Q and implication occurs second? We still have P implies R. We still have Q implies R. P implies R. Q implies R. But now the conjunction disjunction flips over. Any guess on why?
Because the first half is knotted based on our previous definition of implication.
Right. What is this? What is an implication? It's not the first. Right? And so that allows us to say that, oh, wait. That would mean that De Morgan's is somehow going to be involved in this, and that's why it does it. But for the other one, it's okay. So we actually have 4 distributions. We have what if the implication's on the left does exactly what you see. What if the implication's on the right? It does, but we got to flip the and the or. All right, the last one that we haven't done now is biconditional, and there's 2 biconditionals that we should understand. We should understand that P if and only if Q is logically the same thing as P implies Q and Q implies P. Now you can see why we use the operator we do. We picked that operator knowing this logical equivalency. And then we also have a form of, since both of these are logically equivalent to, P implies Q is logically equivalent to not Q implies not P. Q implies P is logically equivalent to not P implies not Q, but that's just a biconditional again, so that tells me that P if and only if Q is the same thing as not P if and only if not Q. There are some others that are in the textbook. They don't even get names, but they're just ones that you may run into. These are the more classic ones. All of these put together, especially this one right here, gets to a question of how do I show logical equivalencies? You know, like what's the purpose of them, or how do we go through them? show something is logically equivalent to something else. Use some open symbols instead of P and Q. If I have a left and right and I want to show that they're logically equivalent, we are going to have three primary techniques for this. One, show by truth table that the left, whatever it is, biconditional with the right as a single compound proposition is a tautology. Just make a really big truth table, show it you have a tautology. The second approach actually has two. And what this does is it gets down to this statement right here. The statement allows me to say that if I'm looking for this thing to be a tautology, that means the same thing as the knots also have to be a tautology, kind of in a parenthesis here. What this really says would be, if you want to show things are logically equivalent, you only have to look for one truth value. Because if you can handle the truths, the only other possibility is false. So what you could do is just say, is the left and the right always true in the exact same conditions? And somebody says, well, what about the false? Well, that's just opposite that, right? So you have two possibilities. You ask, when is this false, and show that they both happen always at the exact same time. When is this true? And you show that it happens at the exact same time, and you pick one or the other. It doesn't matter which. So possibility A is show that these are true in same, probably should use the word exact, same conditions. B, show that they're both false in exact same conditions. This usually falls into a verbal argument. So for example, how could I show that P implies Q is logically the same as not P or Q? And it says pick one or the other. All right, P implies Q. What's special about it? What are the rows? If I would make the truth table and we did it in the proper order, you would see what? True, false, true, true, right? What seems to be its most unique condition? False. It only occurs once, right? So I'll focus on false. When is an implication false? When P is true and Q is false. That's the only time the left-hand side is false. When is the right-hand side false? Why? Because under disjunction, right? The only way for an or to be false is if what? Both the left and the right are false. In other words, I would need not P to be false and Q to be false is the only time a disjunction would be false. But that would tell me P must be what? True, and Q must be false. That's the only time this disjunction could ever be false. Is that the exact same conditions as the left? Yes. You're fine. On the other hand, you could have made it more complicated. When's the left true? When P is true, Q is true, or P is false, and I don't care about Q. Right? Let's look at the right-hand side. When's that true?
When Q is true or Q is false.
But is that the same conditions? It would be under or, it's going to be true if one or both of the sides is true. If the left-hand side is true, what does that look like? P must have been false. And if the right-hand side was true, what does that mean? Q is true. Or both. And so, is that the exact same conditions? Yes, there's three conditions for the left, there are three conditions for the right. They're the exact same, so they have to be equivalent. It's a verbal sentence-by-sentence argument where you're saying, when does this happen and when does the other side happen? Okay, the third possibility is what I did before, is use older logical equivalencies. In other words, what I'm talking about is you start off with, say, you start off with your square and you show by, this is logically equivalent to by some law to, say, step 1, which is equivalent to by some law, step 2, which is logically equivalent to find the right. In other words, what do? You use all of the older laws that you've already proved. Oh, this is the same as this, which is the same as this, which is the same as this, which is the same as the end. Oh, they're the same. Which of the three do you pick? Whichever one you're most comfortable with, or whichever one I tell you. So you need to be able to do all three. What we're doing is, this is classic algebra, right? Symbol manipulation, according to known laws. So for next class, for attendance, do 1.3 from this section, number 23. That does not look like a 23.
Can you explain how we might write out the second, how to show these logically equivalent compared to the, I kind of understand how
What, part 2?
Yeah, part 2.
The words that I said is what you would actually write.
Okay, so I say
It is
I only need to
sentences.
check false because I know that
False would be the most unique one to check
Okay.
because of the left, therefore I will do that.
Okay.
And so
So it's
you
like
usually,
a-
you pick
a
one and
sentence
say
explanation.
why,
Okay.
and then ask for the conditions, and then show it works for the right side as well. Yeah, part 2 is an argument, and you have to write down the argument.